because there's nothing in there, so there's very little gravity. So the universe is expanding much faster than outside the void. So when you do this model, this void is embedded in another bigger universe called the Einstein de Sitter universe. And so the universe is not accelerating. It's an illusion. There is no dark matter. There is no cosmological. Now, one of the problems with the cosmological constant, the standard dark energy model, is that the acceleration of the universe from the data begins to dominate the expansion of the universe when living creatures appeared on Earth. And this violates the Copernican principle, because I said earlier that the universe is supposed to be homogeneous and isotropic, and we're not in any special place in time. The void model, I have to be near the center of this void, which is a spherically symmetric void. So I have to be, if I'm not within 1%, 5% of the center, I can't agree with the data. So this is a violation of the cosmological Copernican principle in space. So the two models that describe the data violate the Copernican principle. It means that we're in a special place in the universe. And this is really weird, okay? And it gives me sleepless nights worrying about it. And other people, physicists, worry about it. They're in denial, a lot of them. They try to ignore it, but you can't ignore it. Okay, so finally I'll finish with some comments about black holes. As we all read in the New York Times or the Globe and Mail or whatever your popular newspaper is, black holes are discovered every other month. And it's become a household word. If you modify Einstein gravity, you will modify what we know about black holes. Because a black hole, as popularly understood, that is, it's a massive object, like we have at the center of our galaxy, and the object has 3 million times the mass of the sun. It's massive. We know it, that it's there. Observation. What is it? Is it an object with a horizon, so that if something falls through the horizon, even light cannot escape the black hole? Or is it something else? So if you modify Einstein's gravity, you're going to modify the solutions of describing these massive objects. And I'm working at present on this problem. We can't get close enough. The best thing to do is to get a spacecraft and fly out to the black hole and throw a ball at it, a baseball, and see if it bounces off. Because a horizon doesn't have, it's not a surface. So if you go on a horizon, you knock on it. Your hand just goes, there's nothing there, okay? Whereas if it's a surface like a star, you could knock on it. So, but we can't get out there. I'm too old to get out there and see the horizon. We don't know the nature of black holes yet. People who do make these observations agree that the evidence for Einstein black holes is circumstantial. Conclusions. So I've tried to explain, hopefully understandable way, how my modified gravity works, what it is, and the distance dependence of the strength of gravity that comes out. Gravity is stronger as you go from the center of a massive body out into the universe. And this means that you can fit the data without dark matter. And we've published data that fits for over 100 galaxies. It's quite remarkable. You gave me the mass of a galaxy, the mass to light ratio. This is the mass divided by the luminosity of the galaxy. And I can predict velocity curve that fits remarkably well without adjustable parameters. And dark matter models cannot do this. For a dark matter, typical dark matter model that fits a galaxy, in addition to the mass to light ratio, there are 2 or 3 other parameters that are different for each galaxy. So for 100 galaxies, you end up with something like 300 parameters, adjustable parameters. This is not a theory. I have a theory. The theory has to predict results. We fit the bullet cluster, as mentioned, without baryonic dark matter and the lensing. You see the acoustical power spectrum and the matter power spectrum can be fitted. Now, in particular, the cosmology that comes out from solving equations is interesting. There's no singularity at t equal to 0. There's no Big Bang. The universe evolves eternally. And you have 2 mirror universes, one for positive t expanding and one for negative t. And there's a reversal of the arrow of time. The time.
Absolutely fascinating. With your equation, do we need to re-evaluate or recalculate the age of the universe if we define, according to your model, the age of the universe at that bounds? Is the bounds the same age of what we call the singularity and the Big Bang?
That's a good question. In the standard model cosmology, the so-called lambda CDM cosmology, lambda is the cosmological constant. CDM is called dark matter, as explained. It works very well, but you have to remember that it has 8 adjustable parameters, and it's a model, okay? And it violates the Copernican principle. So, in that model, when you calculate the age of the universe, it comes out at 13.7 billion years. Now, when you measure the age of the universe, you do it through observations of these globular clusters. And the globular clusters can be as old as, there's an error bar, so-called. I mean, it could be 14 billion years, it could be 12 billion years. This makes me very uncomfortable because globular clusters consist of stars and you have to evolve them. It needs time to evolve these stars. So this to me is a big problem. If you don't have a cosmological constant, and even with cold dark matter, the age of the universe comes out at 11 billion years, which is ridiculous because the universe is younger than the globular clusters, or even radioactive decay measurements on Earth. This is stupid. Yeah. It's called the age of the universe problem. In my mock, you can push the age of the universe t equal to 0. There's no beginning, there's no creation, so to speak, in this eternal universe. T equals 0 is a marker, okay? So you can push it back and get an older universe. In my void model, you can get an older universe. So that's the status of the... I can't answer your question because we don't know.
If we are part of a galaxy cluster, there are other galaxies, other galaxy clusters not that far off. Just what does it mean to say we are at the center of an immense void?
Good question. Well, we know voids exist, we see them. So we could be in a void, okay? And we have to be near the center because otherwise you get too much what's called anisotropy. You begin to violate the isotropy principle too much. You can't agree with the data, the cosmic microwave background data. So we violate the Copernican principle in this model. But you can't rule out the model because it fits the data.
Well, somehow the Copernican principle, I need some water, reminds me somehow of the old idea about uniformitarianism, in geology. why would the Copernican principle be sacrosanct? That's what I mean.